But that's an important outer boundary. Of course, gray matter and white matter is mostly obvious. So the gray matter is your cortex, that's on the outside of the brain, and most of the inside is white matter. It's actually fatty myelin that is wrapped around the axons of the neurons in the cortex, and it's basically kind of like your information superhighway. You know, it's the path out to the body and in from the body. Is mainly conducted through this white matter stuff, and regions are sort of cross-talking through white matter stuff. You can think of white matter as sort of connections. And then you have this stuff even below the white matter. It's more gray matter. So that's like the caudate here, putamen, and these are sort of very obvious structures that will stand out and sort of help you know where you are in the brain if you see these. You know, you're about in the middle. So, basal ganglia ventricles. All right, so some of you may or may not know your brain is actually hollow. It starts from a tube and grows around that. And so these holes in the middle, those are supposed to be there. They're called your ventricles. It's where CSF is produced, cerebrospinal fluid. It's this stuff is the choroid plexus, and it produces this stuff, and it flows, you know, down through this hole here. That's your fourth ventricle. Flows down into your spinal cord and out into your body. In most cases, one thing that can happen is that these can get blocked. And the ventricles can change sizes. And one of the more famous things that has happened with this, so this French guy he's a civil servant, and he had hydrocephaly as a kid. Hydrocephaly is when you get this blockage and too much CSF. And so there's this sort of very popular thing. Man works for, I can't read. A man without brain has worked for government for decades. And you can see here, compared to the normal brain that we were just looking at, his ventricles are quite large. And this person apparently had more or less a normal life. He had kids, family, held a job. He went in for leg pain and got an MRI and showed this. The point is that these will change, and you'll see that pathologically. You'll see that. But this is a fun one to show your friends. You can find this Google civil servant no brain. You'll get that. So, all right. Optic chiasm. That is where your optic nerves coming in, from right and left, across. You keep going to the back of the brain. And that makes a cross, just like that. Can you see right here where that... So these... I'll go all the way down to the eyes here. Okay, so those are the eyeballs, and those are the lenses. And as you come up, you can see the optic nerve here, coming out. You follow it right there. It makes a cross. So that's a really good landmark where you can say, okay, that's where we are. We're at the bottom of the brain. It crosses at the bottom of the brain on the ventral surface. Yes?
Is there any particular reason why we use this template as opposed to another one, which is calling to back, the one below?
Yes, brain said so. It's one of those. It's one of those things where there are lots of templates out there. So and there's lots of different ways to do this. I know that Damasio's have a template. There's a lot of different templates. A couple different ways to do this. Dan.
A little more detail than that.
Good.
The column to bed is that brain, the SFL brain culture tool. It's in the same space. It's a prettier because it's installed. Right. Because you just mentioned that it's tricky to figure out that do a in this template.
Right. Well, you're going to have that same issue with the bet, I think. Did they take out the dura?
I mean, it's supposed to, but there's always a little error right at the edges for bet. So actually, this is better if you really don't see the whole thing. But those edge boxes are not really going to do anything.
Okay. So no, there's not really a very good reason, but it's kind of what we decided. So anterior commissure. This is so these commissures are your you have your right hemisphere, your left hemisphere, and they do a lot of independent work, but they need to talk to each other. So there are these white matter tracks that cross over, and they make for very good landmarks to tell where you are. So that's the anterior commissure there. You can see where that white matter track scoots right across the hemispheres. Another commissure you guys are probably more familiar with is the corpus callosum. So that's the front of it, that's the back of it. And as you come up, that's, the part in the middle where they're, these hemispheres are obviously talking to each other because they're connected. So, and then finally the hardest one to find for me anyway, when you get up to this level, you see all the internal stuff is more or less gone. You don't have nice basal ganglia or ventricles or anything. From here up, it all kind of looks like wrinkly brain. So, one thing that kind of jumps out is the hand motor knob, and let's see if there it is, right here, and over here, and it just kind of looks like this knob. It's kind of the best way. It kind of just juts out like that, and that's your is it lateral fissure? Central. So that's your hand motor. Oh wait, no, that's hand motor. Yeah. Actually, it's always further back than you think it is. Well, it's one of these two. In any case, that's why I said it's a tough one. It's like, oh, it's a lump among many lumps. So, so that one's not as useful. But so there you go. So those are kind of the landmarks to know where you are in the brain. The bottom of the brain, middle of the brain, top of the brain. Okay, so now we can overlay some templates to sort of get maybe a better idea of where we are. And what you do is overlay. And you just add. And then you have to actually find the where your template is. Pretty sure it's in Program Files and MRIcron. Templates, and let's take a look at Brodmann because that's what everybody looks at. Okay, so now you have this overlaid. You can change your transparency so you can actually kind of see what's underneath there. And you can see that, yes?
I'm lost. So what were you just looking at before you found were you not looking at the column brain just before that?
This is the column brain.
What you were showing us, demonstrating on, was the column brain.
That's right. Those landmarks were all in the column brain.
Did you get that through template when you first opened it up?
No, those are just things that you can, like, without any templates, just from knowing neuroanatomy, you should be able to kind of tell where you are
So
in the brain.
You can get it there. Okay. But now, when you went to overlay,
Yes.
was there not CH2 there too?
No, so one thing, if you just do the open template, which is kind of the most straightforward way to do it, it opens it up by itself.
Okay.
And what you want to do, and that's useful for some purposes, but it's more, I think, it's more useful to see it overlaid on the actual brain. So to do that, you have to do overlay add. Okay, and then you can change the transparency so you can see it. But it still has this feature where you can, whoops. It has this feature where you can sort of, click in a region and it'll tell you, that's 37. Now, some of you may be wondering, why is BA37 extending into the cerebellum? Well, it's because it's not a very good map. And so there are problems with it. That's why I said at the beginning, use at your own risk. I mean, it gets a little crazy. For some regions, it's okay. For some, it's kind of crazy. So if you got this big gray one here, 48, which is not even a Brodmann area. So there you have it. You can use this at your discretion. And then you can close it. And you can do the same thing with the anatomical, which is a little bit better, but still use at your own risk. Okay. So now that we kind of have a sense of where we are in the brain, how to open templates, how to, look at things using MRIcron, obviously the brains we get are not quite as pretty and nice as this. We get lots of different kinds of brains. Let's see, what's the best way to do this? Save, no. So for instance, some people have like really long kind of football-shaped type heads. You saw the last one was a lot more round. Like as I said, Colin has the most average brain. We don't see the most average people. You know, some people have weird-looking brains. It's just a natural thing that makes us all like special. So, so one of the things that we have to do is, you know, that's why we do all this warping and stuff, and you're going to hear more about that next week. But it's just something to be aware of, that, you know, when you see something, don't freak out. That's kind of what the whole warping thing is about. And of course that, you know, will introduce noise into your results. And the idea is that, you know, you don't want to sort of overinterpret any single millimeter voxel, because it's not clear that, you know, that one mapped exactly to the same one in Colin, and vice versa. The point is there's some noise, and you should be careful in your interpretation. You're not actually doing an analysis with the resolution on the millimeter scale because of noise, because of lesion smoothness, and things like that. So, sort of the normal thing to do is, you know, what we have to do is get from this, and we have to produce a lesion map shape that looks like this. And I'm going to overlay. That's actually pretty good with the, whoops. Okay. You can see that? Okay. So,
explain yet about drawing in native space versus on the template.
Right, no, I haven't talked about that. That's good.
We talked about that last week.
Did we talk about that? Okay, so that's a good disclaimer. This only obviously works for MRI scans that are clear and you can draw directly in the native space, the scan itself. For CTs or clinical scans where you have less resolution, what we have done is to basically open the template side by side. Trying to think of, can I open a new window here? Okay, so what we would do, I'll put this in axial, sorry, display axial, and so if you aren't drawing in native space, what you want to do is sort of match up your template to your actual scan, sort of as best you can. You can rotate these things, and we decided only to rotate it in the pitch direction. I don't know why. So, in any case, but the point is, that's the landmarks sort of become even more important when you're doing this stuff, because what you want to do is you're like, okay, there's some fourth ventricle there, a little cerebellum there. We're at the, let's see, something about there. So you can see that this is not quite pitched the same, because you got some eyeballs up here, but no eyeballs here yet. A little more cerebellum here, a little less here. So the idea is that you kind of try to match these up, and then what you would do is you do this thing that we call the Wimbledon method, where you look over here and you kind of try to do something like that. And you just kind of try and go back and forth, and you do that slice by slice.